So DeepSeek had made, the version 3.1 had made big waves in recent weeks. I went on YouTube many times and people have many takes on it, and mostly positive. Testing of that model and doing it against benchmarks, against other models, shows something, but people are giving it more credit, I would say, and I would trust in many cases the actual people testing it. So for example, people say that it beats the Sonnet in coding, while they themselves, the DeepSeek team that put out the technical paper, say it's not the case. The other thing is that it's super cheap. So people are making jokes about it, that you put actually $2 and you do a lot of testing on it, you do lots of work on it, lots of flows using the API of DeepSeek, and in a month your $2 will be 1.9 something, so you didn't actually consume any money there. Now, it made big waves when people understood how much the cost was to train that model, which is 600 plus billion parameter model. And the training cost them $5 million only. Now, I'm not sure what the cost was for O or the Sonnet models, but I guarantee you it's $500 million plus. At least this is what I know. Correct me if I'm wrong, but I know it's in that kind of range. And even people now are talking about Grok 3, that it's estimated to be $1 billion plus to train that model. And they've done something, even if it's not better than those models, but definitely neck to neck in many tests or benchmarks, and they trained it with the cost of $5 million. So it was a shocking turn of events, I think, for many people looking at China and what they do when it comes to AI, but definitely China not having access to the state-of-the-art GPUs, maybe not to the scale that they want, at least Chinese businesses. They had to innovate, and they did something that helped them train such a model at a low cost with a really fast inference, a really cheap inference, and a model that really can, in many cases, and based on many people who are testing it, can compare to 4.0 and the Sonnet 3.5 new model. So how did they do that? Today, we're gonna go into that paper, dissect it, see what kind of model architecture they implemented, what kind of methodologies to pre-train, train, fine-tune. We'll understand that then and there when we look at the paper. And as usual, I'm gonna take you through some concepts just to plan for that kind of focus on the paper, and then we'll go through the paper to see really what they have done that is so breakthrough that achieved these results for DeepSeek version 3 that everyone today on the internet, if you go to the internet, go to YouTube, is either using it with Cursor, is using it in automations, in their applications, because it's super cheap, super fast, and super good.
Subscribe to Daddy's channel. The mic.
Okay, so if you look at the screen here, so this is the chat interface for DeepSeek. It's free for now. I don't know if later on they're going to charge, but I guess it's so cheap for them, they can maybe market it by offering the chat interface for free. And I'll have to say, it is advanced. It already have deep thinking, and it already has a search, so internet access. And the interface obviously looks really similar to ChatGPT. And today itself, you can go log in, create an account, and start using it. So let me just give it a quick test, just to show you how fast, how good it is. So I told it, write me the top 5 reasons on why OpenAI 4.0 model is so expensive to train and how DeepSeek V3 beat that problem. So I'll just fix it here, and I put DeepThink, and let's hit go, and you can attach as well. You can search on the internet as I mentioned, but you can attach documents as well. So let's see how see the speed of the inference. I need to explain why OpenAI's GPT-4 is so expensive to train. First off, these models are massive, with billions of parameters. This one has billions of parameters as well. So let's go for the top reasons. Massive scale and complexity, okay. Extensive data requirement. Training a large language model like GPT-4 requires vast amount of data. Collecting, storing, and processing the data incurs substantial cost. High computational cost, okay. Infrastructure maintenance, research and development expenses. Okay, how DeepSeek beat these challenges? Efficient architecture design. So DeepSeek might have employed more efficient architecture design, such as sparse attention mechanisms, quantization techniques, okay, data efficiency. But so it has a good answer, I would say. I don't think it realizes it is DeepSeek V3. This happens with OpenAI many times. I am sure if you used 4.0, if you used definitely O1 is a different scale, you saw the difference in the speed of the inference. It's significantly faster. Again, this is, I'm preferring open models now. So this is an open model. This is why we get the chance to understand what they've done. It's there, you can use it, it's free. Before I move on, if you're not interested to know the price point of DeepSeek and GPT-4o, for example, as a comparison, you're not interested to get an idea about the context window differences between them, or even the concepts, I will have chapters, so you can just jump to the paper. If you're interested in these things, understanding more about the models and the concepts that prepare us to go through the paper, please, take your time and watch them. They are interesting. Otherwise, just jump to the paper and let's go to the fun stuff there. Now, if we move forward, you can go online and with your account, you can actually charge it with money. If you see, I didn't charge mine yet, but don't charge more than $2. You can go online and check what people are saying. $2 will go a long way. So it has an API, which is interesting. So automatically you can deploy it into applications if you like it, if it performs the way you want it to perform, or it's just good enough for the purpose you're developing towards. So you can just go for it. They're even doing a discount on the API that we'll see in a second. So yeah, it's all there. You can do it. You can even look at the documentation. It's all here in the DeepSeek platform. So just go to platform.deepseek.com. I'll put the links in the description. If we go to see the pricing, and here you can tell how cheap it is, and we'll compare it to the 4.0 model cost. So this is the DeepSeek chat endpoint, or the model for the endpoint. And the only thing it is behind 4.0 is the context. So it's half the context length in input and output. Now, if you look at the prices, they put it in this way: input price, cache hit, input price, cache miss, and then output price. And for the hit, it's 0.014 per 1 million tokens. For the miss, it's 0.14 per 1 million tokens. And then the output price is 0.28 per 1 million tokens. Okay, so if you're not looking at these things, it might be, you might be impartial. Even you might think it's expensive. 1 million tokens is a lot. So now when we go to the price of OpenAI, which we'll do now, you will see the difference in pricing. So let's go to OpenAI API details of the 4.0. So this is GPT-4o, you can see here. Okay, so this is GPT-4o model, and you can see the input tokens is $2.5 per 1 million input tokens. And so pricing with batch API, I think the batch API is where you don't get the response instantly. You get it as a batch at a later stage if time of the inference is not so important to you. So you get it at a discount, which is 1.25 per 1 million input tokens. Again, let's go back there just to remember the price. This is at most 0.14 per 1 million tokens, $0.14 per 1 million tokens. If we go back to OpenAI, this is at best price. If you use batching, 1.25 so per million tokens. So is that around 5 times the cost? And for output tokens, so this is the cached one, so it's cheaper basically. And for the output tokens, it's $10 per 1 million output token. When you use the API, if you use it through the batching, the output is $5 per 1 million output tokens. $10. Again, let's go back to DeepSeek, $0.28 per 1 million tokens. How much folds is that? 20, 30 folds more expensive is 4.0. So it really boggles anyone's mind. How did they achieve this? And how does that still make sense for them? And this is what we're going to find out. Okay, so interesting thing. So again, just to understand the downside, if you have a unique case for your application or whatever you're building, the context window for input and output is half of 4.0 for DeepSeek version 3. I think for 99% of people that will not make a difference. The price difference is definitely worthwhile checking that out. But for 4.0, it is double. So if your context is so important, this is definitely matters for you, and probably even going to something like O1 with 200K token window context. Also, if it really like a special use case where you need all of those tokens. So when you say 200,000 token window for the O1, that is around 400 to 500 pages if you put it in a PDF. The same goes here. So you just can imagine, for most people, for most use cases, the context window for DeepSeek version 3 is more than enough. So this is just something to keep in mind. Okay, so now we're gonna start hitting quickly on some concepts that will come across in the paper. So we just look at them, get a high level feeling of these concepts and what they mean, and then we go to the DeepSeek paper and just really go to the parts where it's really something we need to understand to apprehend what they did differently compared to all of the other developers of these models before them, all of the Google papers we looked at in the past, and the obviously the attention is all you need core transformer architecture model that came out. But what later on came from pre-training, fine-tuning, and then multi-shot or few-shot learning, all of these concepts that different companies put forward, like Meta in its Llama model, and then Google with their BERT at some point initially, and then Gemini when they rebranded it to Gemini. So we've seen all of these different, back and forth. They try to tweak things, improve things to make the model smarter. And obviously always they're working towards optimizing the computing requirements for all of these steps for them to be able to deploy such a model, and even the inference itself to make it less costly to the business, less costly to the consumers of the API. So we're gonna look at these concepts, and then we will be able to really break down the puzzle of DeepSeek version 3. So let's go ahead and start going through the concepts and then hit the jackpot in the paper and really understand what they did differently. And I think this is an important lesson. It could be a moment in history. I know it's China. Maybe, people would think, okay, they will be ignored. I think people who are smart enough, at least they will give them the benefit of the doubt and see what they've done differently to get this kind of achievement and maybe try to replicate it, because these models are super, super expensive. OpenAI, and I think any company like Meta, like Google, I don't think they're making profit on these models. They're losing money. It's just a race now. So they have their eyes open towards how do really you achieve a result like what DeepSeek did, to make it at least remotely possible that they make money out of it at some point in the future. Okay, before we go into the concepts that we need to cover, if you think you're advanced and you don't need to really go through that, don't waste your time. Just jump through to the paper so we can go through that. If you think you need to really understand and learn these concepts for you to have an easier time while we go through the paper, please stick around. It's worthwhile if you don't know the information already. Okay, so let's start with the first one. So here we want to look at the concept of supervised fine-tuning. So we've talked in the previous couple of videos, you can go check them out. The last video about the 7 papers that bridge the transformer architecture paper until 2024. So we talked about how different model developers, these companies, they started taking all of that unsupervised pre-training of their model. So basically they dump it with the language and they tell it, go ahead, learn from that language to be able to understand human language. And then it was, some people, here I'm talking about BERT, they took it and they said, okay, we're going to do it bidirectional. And then the next step of that, we're going to take it and then we're going to fine tune that pre-trained model on specific tasks. At a later stage, OpenAI with GPT-3 came in and says, that doesn't work. It's not the way humans understand things. So we're going to pre-train the model like what was being done at that time. What we're going to do is we're going to deploy this few-shot training where we basically give it examples. And from those examples, it will be able to apply its abilities across multiple tasks without doing a fine-tuning per task type of job to develop that model. So all of these are, interesting concepts to know. So here we will talk about supervised fine-tuning, and it will give us an idea what's so special about it and what it means when a model is deploying supervised fine-tuning in a positive or a negative manner. So let's start by looking at this quick visual. So here you have a large unlabeled data set, and this is the pre-training process. And this data, just a dump of language, you can call it that, it goes and they use it to pre-train this model. Okay, so this is computationally demanding. Obviously, if the model has to go through all of these kind of unsupervised data, it's just language, just text, and try to learn from it, it will have to really run at a heavy computational requirement for it to get some kind of learning out of that data. And then once we have that pre-training, this is what we just discussed, we go and get a small labeled data set, okay? And then we use it to fine-tune the LLM. This is computationally inexpensive because it's so clean, the data is so clean, the model can just go through it, fine-tune itself, fine-tune the weights, so it will adjust its parameters to that kind of small labeled data set, which will make it usually able to perform certain tasks, either one or multiple tasks, okay? So this is just the concept that you look at. So let's read this part here. So the success of fine-tuning has led to numerous state-of-the-art results across a wide range of neural language processing tasks and has become a standard practice in the development of high-performing language models. Researchers and practitioners alike continue to explore variations and optimizations of fine-tuning techniques to push the boundaries of neural language processing capabilities further. Okay, so here is the definition of supervised fine-tuning. We're not going to go through this page. Again, I will have the link in the description if you want to read the whole thing. We just want to understand this concept so we can really not struggle when we go through the paper. So, supervised fine-tuning. Supervised fine-tuning involves adapting pre-trained language model, LLM, so the pre-trained model, we get it, to a specific downstream task using labeled data. So we take the pre-trained model, we fine-tune it to labeled data, specific data. In supervised fine-tuning, the fine-tuning data is collected from a set of responses validated beforehand. That's the main difference to the unsupervised techniques, where the data is not validated beforehand. While large language model training is usually unsupervised, fine-tuning is usually supervised. So in supervised fine-tuning, we're dealing with a smaller labeled data, but the big difference, it is validated data. And I assume when they say validated, there's a human or a team going through this data, making sure it's perfectly fit to get the best results out of the model. Now, in unsupervised, it's not validated, it's just data. So that's the main difference. Let's carry on just for these two paragraphs and then we will move on. During supervised fine-tuning, the pre-trained LLM is fine-tuned on this labeled dataset using supervised learning techniques. The model's weights are adjusted based on the gradients derived from the task-specific loss, which measures the difference between the LLM's prediction and the ground truth labels. So the way to think about that, we have labeled data, validated, and you can think about it. It has many forms, but you can think about it as an input and an output pairs. So I have data in pairs, and then I give the input to the model. I see what's the output. I have the validated output already as part of my training data set. I validate it. So I see what the model gave as an output. I see what's the actual output that was part of the data that I prepared and validated, and I see the difference. So we see what's called the loss. And then I adjust the parameter, adjust the weights of that model. Basically, I tweak it to be closer towards the expected outcome. And I've done some videos in the past, you can look them up in my channel, where we actually fine-tune a model based on OpenAI. And you can see while fine-tuning how the chart will keep measuring those losses and trying to reduce them. And along the way, it will be adjusting the weights to get you a better result for the model or a better performance for the model. The supervised fine-tuning process allows the model to learn task-specific patterns and nuances present in the labeled data. By adapting its parameters according to the specific data distribution and task requirement, the model becomes specialized. Okay, So I think we get the idea. So supervised fine-tuning is something that we do to get the model to operate better for a certain task, and we use that through validated, labeled data. Clear? Let's move on to the next thing. Now, I want just to show you high-level things around certain benchmarks, because those are interesting to see how DeepSeek V3 matches or is behind or ahead of the flagship models out there when it comes to these benchmarks. Okay, so let's go for the first one. So this is the MMLU, Massive Multitask Language Understanding. And so let's read here. MMLU, Massive Multitask Language Understanding, is a new benchmark designed to measure knowledge acquired during pre-training by evaluating models exclusively in zero-shot and few-shot settings. We've covered those concepts in the past. Basically, zero-shot, we test the model without giving it any example. Few-shot, we test the model after giving it some examples and get it to train on those examples. So I give it certain examples and I tell it, look at those examples and try to replicate the way you respond in the future based on your understanding of these examples in a nutshell. You can look those up in my previous videos or just go online and look them up. This makes the benchmark more challenging and more similar to how we evaluate humans. The benchmark covers 57 subjects across STEM, which is science, technology, engineering, and math, the humanities and social sciences, and more. So it's science, humanities, in general, engineering, math type of generic benchmark. So it's not purely math or engineering or one of them. So it's I would say it's an interesting way to look at models, and it's apparently fairly new. And usually, by the way, those are a bunch of code. Even you can find them online, download them, and try to train or test a model against them yourself if you have the capacity on your local machine to have a huge model. You can do it even for smaller models if you want to do so. More technical stuff, but you can look it up, you can do it and just play with it if it's your thing. So it ranges in difficulty from an elementary level to an advanced professional level. And it tests both the world knowledge and problem solving ability. So, okay, we get this one. Science, humanities, from beginner to a professional level, we test the models using it. Let's go to the next one, which is the SWE Bench Lit, okay, or Light. So SWE Bench is a data set that tests systems' ability to solve GitHub issues automatically. So this is coding basically. The data set collects 2,294 issue pull request pairs from 12 popular Python repositories. Evaluation is performed by unit test verification using post PR behavior as the reference solution. So this benchmark is a subset of another benchmark basically, which is curated to make evaluations less costly and more accessible. Okay, so just is a light version of a bigger one. And again, this is a way I would say it helps us check the model's ability to solve coding problem. Okay, so let's go to the next one. This is the GPQA. So GPQA stands for Graduate Level Google Proof Q&A benchmark, question and answer benchmark. It's a challenging data set designed to evaluate capabilities of large language models and scalable oversight mechanisms. Let me provide more details about it. Description. It consists of 448 multiple choice questions meticulously crafted by domain experts in biology, physics, and chemistry. So this is biology, physics, and chemistry. It's multiple choice questions. These questions are intentionally designed to be high quality and extremely difficult. Expert accuracy, even experts who hold and or pursuing PhDs in the corresponding domains achieve only 65% accuracy on these questions, or 74% when excluding clear mistakes identified in retrospect. So it's definitely a challenging set of questions, and people who are going for a PhD in their domains of chemistry, biology, or physics, they get like they achieve only 65% mark in that test. So you can imagine how complex these are. Google proof. The questions are Google proof, meaning that even with unrestricted access to the web, highly skilled non-expert validators only reach the accuracy of 34% despite spending over 30 minutes searching for answers. So honestly, it's intriguing. It's something I want to look at and see those questions. Imagine someone telling you, I'm going to give you an exam, you have full access to the internet, and obviously you'll have a limited time. For each question you can go and spend half an hour, and imagine we're talking about 448, and they're saying if you're not an expert and you do that with access to the internet, like the best chance for you to get is 34% mark. So it's an interesting test. I think this is most interesting for me, other than the coding one. AI system difficulty, and okay, this state-of-the-art AI system, including our strongest chat GPT-4 baseline, achieve only 39% accuracy. Okay, so when they did it for the GPT-4, it was 39% accuracy. We know that O1 is much better. It achieved the actual PhD level, I think, of 65%. We will look at these later on. So with this, let's go to two more concepts before we go to the paper. So this is a deep dive into self-attention mechanism of transformers. I will give you the link for this one. I will not go through it because in every video I spend lots of time. It is the essential, it is the heart, it is the core of all the models you see around you. It was based on the transformer architecture model that was put out in a paper called Attention's All You Need in 2017. I keep bringing it because it was a breakthrough. It was so important and still highly influential. So while I will not talk about this, I need to mention that this is so core, so important for anyone who's interested in artificial intelligence to understand, for them to really apprehend anything when it comes to AI going forward. Things are changing around the transformer architecture, but the significant aspect of it is still the same. I have a video I'll keep in the end screen and as a link in the description where we dissect this whole thing and we get to understand it together. So go there, do it. With this, I want to move to a modification or basically a manipulation of that same architecture that is more relevant to present models or future models potentially, and definitely to the DeepSeek V3. So let's go to that concept here. And here we're talking about the MHA, MQA, and GQA, and MLA. So MLA is where we're interested. Regardless, we'll just have a quick look at all of those. Those are interesting concepts to know or be aware of. And later on, it will serve us to really understand the MLA when we go to the DeepSeek V3. Okay, so I'll just go to again, all of these things, I'll give you the links. You can read it at your own pace, at whatever level you want to read and understand. But I want just to get the idea and the hint of on the video of these kind of concepts. So multi-head attention, this is the same one I just covered. I told you to go watch a video. This is the fundamental basic single product attention or multi-head attention when you multiply it, transformer architecture. So I will not go through it. I'll just show you how it looks. So for each of them, there are things you'll have to look at that original concept and understand it. We have, for each input, to simplify it, a query, which is basically the word we want to see against the whole sequence of words and where it falls in terms of attention. We have the keys, which is basically the sequencing of this exact query and the other words within that input, and then the values. Those are the actual values that hold the matrices or the numbers data that tell us the link of attention from one word to the other, here focusing on the query. Okay, so when we do the single product attention, this goes all at once. It's a huge dump of information that keeps going through the model as we train it or fine tune it or whatever. So this is the basic concept. Please spend time to understand it. I'm here maybe skipping this because it will take more time, but it is worthwhile to understand what I'm talking about here. So let's go to the multi-query attention. All of these are different innovations to make this process more efficient, because it's a heavy process. That's for computation, speed, and other aspects. So people tried in many different ways to engineer it to be more efficient. So one of them is multi-query attention, MQA. So to reduce the KV cache bottleneck in MHA, Okay, so this is, I think, the link of the paper that introduced it in 2019. This paper introduced the multi-query attention, MQA, where the keys and values are shared across all the different attention heads, i.e., it's identical to MHA except that different heads share single set of keys and values. This requires a very light KV cache and hence drastically speeds up decoder inference. However, MQA leads to quality degradation and training instability. So what they've done here is they said, you know what, we're not going to keep doing unique keys and values for each query. We're just going to have a common key and value for all the queries that go through the transformer. And with that, we reduce the requirement on the cache, basically the memory, and the bottleneck and computation. Now they say, okay, there's a downside to doing that, which was the quality and degradation in the training and training instability. So it makes things easier, faster, but you don't get the quality model that you're working towards possibly. So this is multi-query. So each query here. So these are the queries. So let's go to the color coding here. These are the queries. All the queries have the same set of keys and the same set of values. Okay. And again, don't confuse that having the same set of keys that they lose that sequencing of the incoming input. It's all put in one matrix, I assume, and it has all of the information all at once, the same information. It doesn't change and modify based on each, run through the single head attention, decoder, encoder process, and the feed forward network, yada, 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 as it goes through. It just gets two matrices that stay standard across the whole process. The next one is grouped query attention. Grouped query attention, GQA, is an interpolation between MHA and MQA by introducing a number of subgroups of query heads, less than a total number of attention heads, with each having a single key and value head. In contrast to MQA, GQA keeps the same proportional decrease in memory bandwidth and capacity as model size increases, as intermediate number of subgroups lead to an interpolated model that is higher quality than MQA but faster than MHA. It's evident to notice that GQA with a single group is equivalent to MQA. So the way I understand it, rather than getting each query the same set of keys and values, actually you have grouped keys and values. So it's like somewhere in the middle between the conventional transformer and what we have here. So the way I see it, it's a middle ground between the conventional transformer where each query has its key and its value, and what we had in the previous one where we have the same key and value for all queries. Here we have sets of keys and values and for groups of queries. So in this visual example, these two queries have this set of keys and values, and the same goes for this group and this group and this group. So this is like some kind of, a solution that is in the middle. So we're not going for the complexity of what we have in the original transformer architecture. And also we're not going to the degradation that we see in the previous one, which was the multi-query attention. So we're going somewhere in the middle that gives us good quality kind of training, but at the same time reduces the bottleneck of the caching for the keys and values. So this is one thing that came. Now, okay, everything here will come with an implementation. If this is your thing, you'll see code around it and how to implement it. I'm not going to look at that. Now, this is what I'm interested in. So I just wanted to give you a quick look at what led us to the multi-head latent attention, which was deployed by DeepSeek. So this is DeepSeek's kind of innovation that they brought in their version 2, still in version 3. So multi-head latent attention, MLA, achieves superior performance than MHA, as well as significantly reduces KV cache, boosting inference efficiency, instead of reducing KV heads as in MQA and GQA. MLA jointly compresses the key and value into a latent vector. So what they do is, in a nutshell, that they do a compression for the keys and values, and later on they, I assume, decompress them, so you get the best of the transformer architecture where each query has its key and value. But as the process runs, you are dealing with compressed matrices that later on get decompressed, so you get the best of two worlds. So we will read a little bit about that, and then we'll move to the actual paper. Just, it's good to understand that, okay, we're compressing the keys and values to make the process easier on caching on memory, so it's faster and computationally it's less demanding. Okay, so low rank key value joint compression. Instead of caching both the key and value matrices, MLA jointly compresses them into a low rank vector, which allows caching fewer items since the compression dimensions is much less compared to the output projection matrix dimension in MHA. Okay, you can dig deeper and deeper into this. The concept to keep in mind, the multi-head latent attention is compressing the key and value to make it just easier to deal with a smaller dimension matrix rather than the big one later on in the process of the decoder encoder on the transformer architecture. So it's an improvement over the multi-head attention in the original transformer that reduces the need for memory and computational power required conventionally to train such a model. Okay, with this, we are ready to jump to the paper, finally, and really look at the significant parts of that paper that show us what did they do so special to deliver such results. So let's jump there without any further ado. And hey, if you're enjoying the video so far, if you're still here, anyways, hit that subscribe button, hit that like button, maybe share it with others who are interested in these kind of papers and geeky knowledge. Basically. So let's go to the paper itself. DeepSeek. Okay, this is, by the way, it's a nice logo. I just like it. So DeepSeek V3 technical report. Okay, so let's read the abstract. I keep saying I always like to read the abstract. Like, there are certain parts of the paper you should read, like the conclusion abstract. So let's start with this one. It just gives us the the feel of the paper and what they're going to drop at us as we progress into that paper. We present DeepSeek V3, a strong mixture of experts. So again, mixture of experts is something we covered in the last video. If you want to go there, go there. It's interesting to understand, and with switch transformers. So it's a mixture of experts language model with 671 billion total parameters with 37 billion activated for each token. So I assume here they're talking about that switch transformer mixture of experts architecture, where not every time there's a token that goes through the model, it goes to go through the whole huge model. It goes into clusters. So there's switching mechanism, and a mixture of experts, what they call, basically is going to smaller groups of parameters that address that certain token, okay? To achieve efficient inference and cost-effective training, DeepSeek V3 adopts multi-head latent attention, which we just covered, and DeepSeek mixture of expert architecture, which were thoroughly validated in DeepSeek V2. So they're telling us these are not new concepts in V3. These are things that they validated, they put forward when they did their DeepSeek V2. Now, DeepSeek V2 didn't get the results this one got. So there are things in their pocket they will reveal to show us what they did even differently in V3 that got the model that we have today. Furthermore, DeepSeek V3 pioneers an auxiliary loss-free strategy for load balancing and sets a multi-token prediction training objective for stronger performance. These are things we need to read on in the paper. So they're talking about auxiliary loss-free strategy for load balancing, and then a multi-token prediction training. So we'll see about these two concepts. We pre-trained DeepSeek V3 on 14.8 trillion diverse and high-quality tokens. Again, I want you to focus on diverse and high quality. So I think one of their tricks up their sleeve when they did this, they had clean data. They had great quality data to train the model, followed by supervised fine-tuning and reinforcement learning strategies to fully harness its capabilities. So we've talked about supervised fine-tuning. So this is when we get validated labeled data. So they did that. And also they employed reinforcement learning stages where basically the model gets feedback to tell it, okay, this is the way to progress, or you need to move in a different manner. Now, some of the reinforcement learning is human, human feedback type of reinforcement learning, but also some type of reinforcement learning is just by going after improvement of a certain metric. So let's say reducing the loss to a certain value and so forth. I think that's what they're talking about here. Maybe I'm wrong, unless they mention later on that human feedback is part of that reinforcement stages that they put forward. Comprehensive evaluations reveal that DeepSeek V3 outperforms other open source models and achieves performance comparable to leading closed source models. Despite its excellent performance, DeepSeek V3 requires only 2.788 million H800 GPU hours. Now we'll see how that translates in human language. But basically, the time they require to train this model was a huge, significant reduction to the conventional similar sized model to be trained. In addition, its training process is remarkably stable. Throughout the entire training process, we did not experience any irrecoverable loss spikes or perform any rollbacks. The model checkpoints are available. Okay, so you can go to this GitHub repo and see the checkpoints for the model. So it's an open source one. This is why it's amazing. They're doing it and they're telling the world, go check out what we've done. Okay, so the models they're putting here in the benchmark, this is the really impressive and interesting part. We have DeepSeek V3, we have DeepSeek V2.5, we have Quinn. This is also a model, 72 billion parameter. This is the Instruct one. So many people are talking about it highly as a smaller model. We have the 3.1405 billion Llama model, which is one of the models also. So many people say it's a super amazing model in terms of performance. We have GPT-4o, and then we have 3.5 Sonnet, okay? And now we're looking at these are the different benchmarks, some of them that we covered, others we didn't. So here we're looking at the MMLU, which is the one talking about STEM, basically, science, technology, engineering, and math. So this is basically generic around science. And here you can see that the only one that beats it is Claude 3.5 at 78 points, while the DeepSeek version 3 is 75.9. Now, if we look at 4.0, this is 4.0 here, is 72. So it's beating 4.0 at this level. It's much cheaper than 4.0 and it's much faster than 4.0. The second one is the GPQA. And remember, the GPQA is like those 400 plus questions that are super complex that even with internet access, non-experts barely get 30 something percent. So here, DeepSeek V3 got 59.1%, and Sonnet still beats it here, getting 65%, and 49.9 for 4.0. So definitely it's let's say top 2 now compared to Sonnet. Now, just to be fair about this, you know, I've seen people give their feedback. Now here, I think they're being transparent. They did all these standard benchmarks and give the results. People honestly are giving it more credit. I said that at the beginning. People say DeepSeek V3 is beating Sonnet in more than what we see here. So here it looks like for the most part, it is going for Sonnet 3.5 as a performance. Online, I'm just getting feedback from people on X or YouTube when they do evaluations. They're saying, actually, we, from our experience with the model, real life testing, so it's not just benchmarking, actually we prefer it in more cases than it's giving credit to itself. I mean, that's maybe less objective than what we see in front of us, but just for you to know. So you can go and check out those for yourself. Now, what's interesting is math. So look at math 500. This is a separate math benchmark, nothing from the benchmarks we covered. It got 90.2%, while the top one here which was Quinn, and see, this is why Quinn is unique. It's a 72 billion parameter model, and it got here 80%, while Sonnet got 78% and 74.6 for 4.0. So it blew them out of the water. And then we have here the AIME. What I don't know the details of this one, but what I know is this is something related to coding. And this is what I see so many people talking about the model. So it ranked at 39.2. Again, correct me if I'm wrong. I know this is again one of the coding related benchmarks. So it blew every other model out of the water. And then we have Code Forces, and this is where it's the same test they do for the best top coders in the world to rank them. So here it's used to basically rank AI models, and basically here this is 51.6 percentile. And this benchmark became famous with O1. That is, they're claiming it achieved the 178th, I think, coder in the world. Like if the score of that coder, the O1 achieved that, or the O3 achieved that. I'm getting, there's so many news, I'm getting confused. So all in all, you look at this chart and you know you're dealing with a special superior model that is worthwhile the time to really understand how it was developed. Okay, so let's go forward so you can go through the content. I'll have the link for the paper in the description if you want to go word by word. I just again want to hit the points that are important for us. So again, one of the parts I like to go through quickly is the introduction. In recent years, large language models have been undergoing rapid iteration and evolution. Anthropic, okay, so they're talking about the other models that they're looking against or benchmarking themselves against. Anthropic, Google, and OpenAI, these are the closed source ones, progressively diminishing the gap towards artificial general intelligence, AGI, beyond closed source models, open source models, including DeepSeek series, DeepSeek AI, okay, so these maybe the previous versions, Llama series, and others, and then Quen, Mistral, okay, also making significant strides, endeavors to close the gap with their closed source counterparts. Okay, so just high level that, all of them are going towards one goal and they're making big movements, big improvements. To further push the boundaries of open source model capabilities, we scale up our model to introduce DeepSeek V3, a large mixture of experts MOE model with 671 billion parameter, of which 37 billion are activated for each token. Okay, so just a high level about what they're doing here. Let's go to the areas I highlighted, which probably are the important one. So beyond the basic architecture, we implement two additional strategies. Okay, this is what they did differently from V2 to further enhance the model capabilities. DeepSeek V3 pioneers an auxiliary loss-free strategy. We read about it, and this is, I will assume, a paper that talks about this strategy for load balancing with the aim of minimizing adverse impact on model performance that arises from the effort to encourage load balancing. Secondly, DeepSeek V3 employs a multi-token prediction training objective, which we have observed to enhance the overall performance on evaluation benchmark. Okay, still didn't go to the weeds of it. In order to achieve efficient training, so it's all about efficiency here, we support the FP8 mixture precision training. So it's all about efficiency for the Chinese company behind DeepSeek. Its evolution being closely tied to advancement in hardware capabilities. Again, other papers spend more time if you like these things. I'll just cover the important part here. In this work, we introduce FP8 mixed precision training framework, and for the first time, validate its effectiveness on an extremely large-scale model through the support of FP8 computation and storage. We achieve both accelerated training and reduced GPU memory usage. As for the training framework, we design the dual pipe algorithm for efficient pipeline parallelism. Okay? So if you didn't get that from my slang, which has fewer pipeline bubbles and hides most of the communication during training through computational communication overlap. This overlap ensures that as the model further scales up, as long as we maintain a consistent computation to communication ratio, we can still employ fine-grained expert across nodes while achieving a near zero to all communication overhead. In addition, we also develop efficient cross-node all-to-all communication kernels to fully utilize infinite band and NVLink bandwidths. Furthermore, we meticulously optimize the memory footprint, making it possible to train DeepSeek V3 without using costly tensor parallelism. Again, combining these efforts, we achieve high training efficiency. Okay, there's so many things to unpack there. We're gonna hit the important ones later on, but it's just, okay, good to see that they have mechanisms, at least I remember 3 of them, that they deployed differently in the V3 to get this kind of optimized training for this model and obviously high quality performance. Okay, let's carry on. During pre-training, we trained DeepSeek V3 on 14.8 trillion high quality and diverse tokens. So this is the number of training data, or the size of the training data, 14.8 trillion high quality. This is, I think, very key, high quality and diverse tokens. The pre-trained process is remarkably stable. Throughout the entire training process, we did not encounter any irrevocable loss spikes or have to roll back. Next, we conduct a 2-stage context length extension for DeepSeek V3. In the first stage, the maximum context length is extended to 32K, and in the second stage, it is further extended to 128K. This is interesting. Following this, we conduct post-training, including supervised fine-tuning and reinforcement learning on the base model of DeepSeek V3 to align with human preferences and further unlock its potential. During the post-training stage, we distill the reasoning capability from the DeepSeek R1 series of models, and meanwhile carefully maintain the balance between model accuracy, let's carry on and we'll go back to the table, and generation length. We evaluate DeepSeek V3 on a comprehensive array of benchmarks. Okay, so these are the benchmarks we just covered, and it just tells you how it measures against those open source and closed source models. Here they're talking more around the training. So this is, they actually trained the model in 3.7 days on our cluster with 2048 H800 GPUs. So they used this cluster, and I wouldn't say it's the biggest in the world. It took them only 3.7 days to train the model. Consequently, our pre-training stage is completed in less than 2 months and costs around 2,664,000 GPU hours, combined with 119,000 GPU hours for context length extension and 5,000 GPU hours for post-training. DeepSeek V3 costs, okay, so they're talking here about the cost of training the model all in all, which is 5.5 million. Let's look at the table. So this is in H800 GPU hours, and this is in USD. So pre-training cost them this amount of hours, which we covered. The cost for pre-training this model was $5.3 million, and then around $230,000 for the context extension, and post-training it was around $10,000. So all in all, the model cost DeepSeek to pre-train, context extend, and post-train $5.5 million, which is a fraction of the training cost for any other model out there from the ones they covered, especially the big ones with similar size parameters. And here their calculation is assuming that the rental price for the H800 is $2 per GPU hour. Okay, that's clear. So let's jump quickly to the top concepts that they deployed to get this model forward. And again, we're going to focus on the things that they did differently, not the whole thing, because some of the things we already covered as concepts in the past. We want to see what they did differently to really understand what makes it special. So let's start with, again, all of these, when you go through such papers, you'll see that, they bring it at certain level of complexity and then they add more details. So we're unpacking kind of the knowledge that we have in the paper step by step. So you have to be patient, but if you enjoy this thing, it will be also fun as you follow along with me as we unpack, the onion basically of this model, the layers, to get to really the heart of it, of why they and how they did something so great. So architecture innovation, so load balancing strategy is one of the things they focus on as significant to the performance and training objective. On top of the efficient architecture of DeepSeek V2, so they're referring to that architecture, we pioneer an auxiliary loss-free strategy for load balancing, which minimizes the performance and degradation that arises from encouraging load balancing. We investigate a multi-token prediction objective to prove, okay, we need more information about that. We design an FP8 mixed precision training, which we already covered. They said it already. So we're talking about load balancing, multi-token prediction, FP8 mixed precision training framework. So these are the three things. Anything else, DeepSeek people? Through the co-design of algorithm frameworks and hardware, we overcome the communication bottleneck and cross-node mixture of expert training, achieving near full computational communication overlap. This significantly enhances training efficiency. Okay, so this is, we know, mixture of experts is a concept that is well known. And economical cost of only, okay, again, they go over the cost. So three things I think we need to really understand out of this paper. The first one is the load balancing strategy. The second one, the multi-token prediction. And then the third one, what they did with the FP8 mixed precision training framework. Okay. And then they talk about post-training. We introduce innovation methodology to distill reasoning capability from long chain of thought. So again, they're deploying the concept of chain of thought, which we know is there in O1. Specifically from the DeepSeek R1 series models into standard large language models. Okay, so they're just talking about that. So summary of core evaluation results. We've seen the results high level. We don't need to dig deep into those results. So let's get past that and hit the architecture. So let's read the basic architecture. The basic architecture of DeepSeek V3 is still within the transformer. This is the paper of attention is all you need. So this is why I said at the beginning, it's very important for you to really dig deep in that. I have a video which is popular for a 2.5 hour video. It has more than 3,500 views. Go there. There's many sources online other than mine. If this is not your taste, my style, and if it's longer than others, just understand it. Get it through your head, really digest it. It will help everything else as you try to understand these models. So for efficient inference and economical training, DeepSeek V3 also adopts the multi-head latent attention, which we just looked at high level, and the DeepSeek mixture of expert architecture. So these are well-known concepts. We understand them now. We have been thoroughly validated by DeepSeek V2 compared with the DeepSeek V2. An exception is that we additionally introduce the auxiliary loss-free load balancing. So we said this is the new thing. We need to understand it. And then we'll go back to the diagram. And then we want to understand the DeepSeek MOE, which I think we understand. Okay, but we'll look at it if they cover it. Also, okay. So they're focusing on the load balancing. So let's see, we'll get to that. So this is, let me just a little bit zoom out for you to see the whole diagram at one shot. I think this should be clear here. So this is the architecture. Now, again, I keep saying it, I know, I'm sorry. Go back and understand the transformer architecture. But basically here they're focusing on the latent attention. This is the attention block, let's call it that. Here you have some normalization that has to happen for the incoming tokens and their details. But basically, again, I'm not a super expert in this, but I will tell you here, whatever they're covering here is basically how they're compressing the keys and the values that goes to the standard multi-head attention. So they're dealing with a much smaller matrix, and then they push it through the hidden feed-forward layers. And after that is happening, it goes to the feed-forward network again here. So this is the network of the model. And here they deploy the mixture of experts. Maybe I mentioned it, I am wrong. There's no switch transformer here. So, or is it considered a switch transformer still with this way? What I understand is within a switch transformer, there is multiple mixture of experts that you can deploy. So if you know more about that, write me a comment in the comment section. I will definitely look it up later on. But they are using these 37 billion kind of clusters of the parameters of the whole 671 billion parameters. So every token that goes through the network doesn't actually go through the whole model. It actually goes through a router of some sort that will send it to one of the experts, which is, so you can see the blue is a routed expert, and then they have something called a shared expert. So okay, so some tokens go to these shared experts and the other part goes to just one of the routed experts. So just a single cluster of these parameters rather than the whole thing. So at best, I think a token, as I understand it from the visual, will go through 37 billion parameter clusters or experts within that architecture, and then it goes to the feed-forward network normalization, yada yada. You get out at the end of this the prediction, I assume. Okay, so let's carry on. So just to get an idea, high level, you know, these things is very important for you to really digest. You don't need to be really detailed in your understanding of the equations and everything, unless this is something you want to do. But at least today, if you understand these concepts, you can talk to it. You can understand what's happening and how these things are evolving and the breakthroughs that are happening. So you'll understand, okay, this is why this model is so special. So, okay, let's spend a little while reading this. Definitely they're sharing all the math behind it. Let's read what they say about the multi-head latent attention. So for attention, DeepSeek adopts the multi-head latent attention architecture. Let D denote an embedding dimension. So you see they're talking about the dimension and how it will be compressed. Denote the number of attention heads. Denote the dimension per head. Okay, so this is the equation. Denote the attention input. Okay. The core of MLA is the low-rank joint compression for attention keys and values to reduce key value cache during inference. Okay, they have some of the equations here. You can read more about that if it's your kind of thing. I think it's fun if you want to really dig deep and understand how the math works. There are resources. If you go to their repository, I'm sure they're going to have the code to how to implement this if you're interested. So here they go through the whole calculation and even going to the softmax. This is part of the basically this is where the running of all of these matrices happen for the attention and the softmax function. So ultimately attention queries, keys and values are combined to yield the final attention output. So this is the equation that gives us the final attention value and output in the matrix. So again, the calculation and concepts behind the mixture of experts. For feed-forward networks, FFNs, DeepSeek V3 employs DeepSeek mixture of experts. Compared with traditional mixture of experts architecture, DeepSeek mixture of experts uses finer-grained experts and isolates some experts as shared ones. Okay. Let you denote. So this is what we saw in the architecture. So the mixture of experts doesn't usually have those shared experts. They did something differently. There's a reason behind it. Maybe we'll get a hint of it. But basically you have the experts that based on the router, the token will go to a certain expert or cluster of parameters. This is at least how I understand it in my brain. And then there are shared ones that many tokens go through, or I think every token will have to go through one of the shared experts. Okay, so here they carry on the calculations of the mixture, at least their version of mixture of experts. Interesting part, again, we covered that in the past. They use the sigmoid function to compute affinity scores. Again, this is the activation function within the feed-forward network. And okay, so let's slow down here, because this is a new concept to me. If you watched my videos previously, probably it's a new concept to you. So let's slow down and just see what they say about the auxiliary loss-free load balancing, because this is the topic I don't know. And maybe later on, as we peel the onion, we'll get more information about that. For mixture of expert models, an unbalanced expert load will lead to routing collapse. Okay. And diminish computational efficiency in scenarios with expert parallelism. I hate saying that word. Conventional solutions usually rely on the auxiliary loss to avoid unbalanced load. However, too large an auxiliary loss will impair the model performance. To achieve better trade-off between load balance and model performance, we pioneer an auxiliary loss-free load balancing strategy. to ensure load balance to be specific, we introduce a bias term BI for each expert and add it to the corresponding affinity scores to determine the top K routing. So the way I understand this, I know it's a lot to pack into paragraphs, but the way I understand it is that when you deal with a mixture of experts, so let's really imagine them as experts. So when you deal with experts, we're throwing tokens across these experts, right? And in theory, the load should be equal across all experts for the model to operate well. Now, apparently, there is a case where in certain scenarios, what they're calling the routing collapse happens, where I assume an expert is overloaded compared to others. And if this happens, it will diminish the computational efficiency in such scenario of the expert parallelism, which I assume is not actually, things are not happening and so really in a balanced way between those experts. Now they say in a conventional solution, so they had this problem in the past in the standard mixture of expert kind of architecture, and they solved it by the rely on the auxiliary loss. The way I understand it, it's a kind of loss they force into the system to somehow reduce the possibility of such routing collapse. But this apparently also is not really working because if that happens, the way, again, I understand it, it might shut down certain experts and then certain other experts will have a higher load, which will impair the model performance. So the loss, if it keeps being applied to a certain bunch of experts, that will lead that actually the other ones will be overloaded. So it will affect the performance of the training, performance of the model in general. What they've done is, yes, while they call it auxiliary loss-free load balancing strategy. So this is the strategy to balance the load between the experts. So now it clicks in to understand. And they do this way by actually, rather than introducing loss only, they introduce also a bias. So the bias, I would call it like something that would re-energize, reactivate the experts that are facing maybe too much loss because they're not balancing well. So they use a balance to reactivate them and keep the expert architecture balanced in terms of tokens received and loads being processed through that mixture of expert feed-forward network. I hope I didn't butcher the concept. This is how I understand it. Now there's an equation behind it, so this is the math behind it. But for me, it makes sense, at least. And this is the easiest way to address these things. I will do it is read more about it and just ask a model like ChatGPT, ask it to explain it for a 10-year-old. Probably you'll get a simple way, but I think I understood it right. Note that the bias term is only used for routing. The gating value, which will be multiplied with the feed-forward network output, is still derived from the original affinity score. Okay, during the training, we keep monitoring the expert load. So they're looking at the load to make sure that it is balanced. At the end of each step, we will decrease the bias term by Y. Okay, so they're decreasing the bias if its corresponding expert is overloaded, and increase it by Y if its corresponding expert is underloaded. Okay, so they're using a coefficient called Y to either increase or reduce the bias. So they decrease the bias if the expert is overloaded, and they increase the Y if the expert is underloaded. Okay, interesting. So I don't know, does that mean that they are not actually pushing that auxiliary loss that they mentioned before? Okay, so if you know the answer, please write it in the comment section. And they're saying Y is a hyperparameter called bias update speed. Okay, through the dynamic statement. Okay, keeps balance. So we understand the first concept. I think this is clear. So the auxiliary loss-free load balancing is just a way to keep the load equal between the experts. I think that includes also the shared experts as well. So the model performance will remain high. It will not face a routing collapse as they have with the conventional mixture of experts. Let's carry on. So here they talk about complementary sequence-wise auxiliary loss. Okay, so no need to go through that detail. Okay, I just removed the highlight of this kind of diagram. I think it wasn't clear. So here they're showing us illustration of our multi-token prediction. So this is the second topic, multi-token prediction implementation. We keep the complete causal chain for the prediction of each token at each depth. So we'll have to read more about that. So let's go to the multi-token prediction. Okay, inspired by, this is a paper, we investigate and set a multi-token prediction MTP objective for DeepSeek version 3, which extends the prediction scope to multiple future tokens at each position. On the one hand, a multiple token prediction objective densifies the training signals and may improve data efficiency. On the other hand, MTP may enable the model to pre-plan its representations for better predictions of future tokens. So the ideal transformer architecture usually predicts one token ahead. So it has the whole context of the input and the output as it comes, and it will keep looking at the context and add one token, add one token, add one token. And the token in the next cycle will become part of that kind of attention span to predict the one after it and the one after it and so forth. So here they're doing it through multiple blocks, as we've seen. So it's deploying, I understand, the same transformer architecture, which has one prediction, but they just do the shift. So they do shifting to get 2 and 3 kind of tokens ahead predicted out of that block. Now, if you go to the transformer architecture, this is why it's important to digest it. They do some masking. So in the encoder decoder part, they do masking for the token that is being predicted from the whole context. And then at some point, after just looking at the attention of the input without the output, so they mask that kind of attention. At later stage, both of them will come together for the complete feed-forward network and normalization to happen to get that prediction based on both the input and what's at that time is being predicted as the output from the previous run. Here, they're doing it in parallel to get 2-3 words at once in sequence as they run the prediction in this architecture. This is how I understood it. I hope I didn't butcher again the concept. But again, you can read it 2-3 times, you'll get it, or just do your own research. But at least I digested this way. Different from, okay, this is the paper that presented the concept of multi-token prediction, which parallelly predicts the additional tokens using independent output heads. We sequentially predict additional tokens and keep the complete causal chain, so it's a chain, at each prediction depth. Okay, we introduce the details of our MTP implementation in this section. So they call them, what we were looking at, the 2 MTP models. So we had the main attention head and the 2 MTP models. To be specific, our MTP implementation uses these sequential models to predict the additional tokens. The kth MTP model consists of a shared embedding layer. Okay, and they talk here about it's all the math behind it. Okay, I'm gonna skip the math. Let's go to the texty part. Our output head, the out head, linearly maps the representation of logits and subsequently applies the softmax function to compute the prediction probability of kth additional token. Also, for each MTP model, its output head is shared with the main model. Our principle of maintaining the causal chain, so it's a chain of predictions, is similar to, again, reference to a paper, but its primarily objective is to speculative decoding, whereas we utilize MTP to improve training. So MTP training objective, for each prediction depth, we compute cross entropy loss. Okay, this is the loss, again, calculations. So let's read this part here. MTP in inference, our MTP strategy mainly aims to improve the performance of the main model. So during the inference, we can directly discard the MTP modules and the main model can function independently and normally. Additionally, we can also propose these MTP modules as speculative decoding to further improve the generation latency. You know, the way I understand it, in simple terms, let's go back to this figure. Okay, so the way I understand it, looking at this, is the conventional transformer architecture will help us predict one word, like what's the next word that we need to see the highest probability it makes, the right choice for that next token or word, just to make things easier. And that happens, by the way, when you're writing in an email on Outlook or in many tools. It will give you like, a prediction for the next word. So this is what you're gonna write next. It's good, but what they're trying to do here, it helps the learning. And if you think about it in simple terms, if you have two more tokens. So let's say if Outlook, I don't know if Outlook does that. I always see one word predicted on Outlook when you press tab and you get that word already, punched in rather than typing it to make things faster. But imagine it's giving you two words ahead as well. So it might get your brain to think differently about how you're writing that statement or that sentence. So if you get three words predicted ahead, you might change the way to how you're writing the tone of that email, or how you're bringing an angle on a certain topic. So it might help you write in a smarter way. So I am assuming here that doing so in the training of the model, also that could be the case. It helps the model be smarter as it is being trained. So this is the whole concept. So they do that through not only having the main model, so they have additionally those MTP models. So two models here, they're showing if this is the actual, maybe there is more. No, they have 3 dots. So it could be even more. I don't know how much, but they have these MTP models that kind of create a chain that could create that kind of sequence of predicted words. And I think the probability would reduce as words go towards the right more, but still it gives the model an idea of, okay, this is probably where this is going as a statement, not as a token, as a sequence or a chain of tokens. Just what they say, doing it this way made it smarter as a model. So that's the second concept already understood. So the MTP, let's carry on. Okay, so this is the third one, which is the FP8 training. So we understand the MTP, we understand the expert load balancing. Now, this is the third secret, which is FP8 training. So inspired by recent advances in low precision training, again, the reference papers, we propose a fine-grained mixed precision framework utilizing the FP8 data format, so it's a data format of some sort, for training DeepSeek V3. While low precision training holds great promise, it is often limited by the presence of outliers in activations, weights, and gradients. Again, references. Although significant progress had been made in inference quantization, again references, there are relatively few studies demonstrating successful application of low precision techniques in large-scale language model. Okay, there's a figure here, we'll go back to it later. To address this challenge and effectively extend the dynamic range of the FP8 format, we introduce a fine-grained quantization strategy, tile-wise grouping with one element or blockwise grouping. The associated dequantization overhead is largely mitigated under our increased precision accumulation process. Okay. A critical aspect for achieving accurate FP8 general matrix multiplication. However, to further reduce memory and communication overhead in the mixture of expert training, we cache the dispatched activation in FP8 while storing low precision optimizer state BF16. We validate the proposed FP8 mixture precision framework on two model scaled similar DeepSeek V2. Okay, this is going over my head. So I'll go to ChatGPT, try to understand it in a simpler way, and I'll try to explain it here. You can do your own research, but at least you'll get the concept out of the video as well. Okay, so I prompted ChatGPT. I told it, I copied paste that whole section. I asked it, please explain it to me as if I'm an 8-year-old. At least I just want to understand the concept. I don't want to really be able to replicate things or go into the details of the math behind it. I just want to understand what I'm looking at. So hopefully also you want to do the same. Otherwise, you can also use ChatGPT and other tools to dig deeper into this. So let's read how ChatGPT explained it to my 8-year-old brain, not understanding this complex concept. Imagine you're solving a huge puzzle. You have a giant puzzle with millions of tiny pieces. This is like training a big model. Okay, normally you'd use big heavy tools to move the pieces around. This is like using full precision numbers like FP32 or BF16 for calculations. So these are number standards, I would assume. These tools work well, but they slow and take up a lot of space. Okay, so it's just data handling. Let's assume that for the numbers, or as the data runs in the model or the weights run in the model. Let's see. FP8 training is like switching to smaller, lighter tools that are faster and easier to carry. These smaller FP8 numbers, so it's a number standard, it seems, still get the job done, but require some extra tricks to make sure they don't break the puzzle pieces, maintaining accuracy. Here's how we make it work, okay? Use light tools where possible. Most of the puzzle solving big math operations can safely be done with these smaller FP8 tools. This makes the process faster and uses less memory. Switch to big tools when needed. For tricky and delicate pieces, like very sensitive parts of the model, we bring out the big precise tools like BF16 and FP32. These parts include things like embedding, attention, and mixture of experts gating models. Using big tools here keeps the puzzle stable. Okay. Group puzzle pieces smartly. Instead of trying to fit the whole bunch of pieces into FP8 tools at once, which can lead to errors, we group them in smaller chunks. This way, FP8 tools can handle each group carefully, avoiding mistakes caused by outliers, puzzle pieces that don't fit easily. Okay. The tricks to make it all work. Adjusting the scale. Imagine in some puzzle we are, okay, so let me just ask it to give it in a more complex, not complex, but more comprehensive manner, and we'll see what we get. Okay, so I asked it to take it up to a university level kind of training. So FP8 stands for 8-bit floating point. It's a way to represent numbers in a computer using only 8 bits. Okay, now it's clear. So it's an 8-bit representation of a number, which is much smaller than commonly used formats like FP32, which is 32 bits, or FP16 or BF16, which is 16 bits. Okay, so we're using 8 bits compared to 16 or 32 bits. FP8 is designed to specifically speeding the computation and machine learning and AI training, which slightly less precision is acceptable. Okay, it's in areas where less precision is okay. Why FP8? Efficiency. So smaller numbers mean less memory usage and faster calculation. Good. For large AI models, this can significantly reduce costs and training time. Good enough precision. So AI models often don't need extreme high precision for most calculations. FP8 is precise enough for tasks like matrix manipulations, which are the backbone of neural network. So all the parts that happen in the feed-forward network, maybe in the normalization, is done through that FP8 kind of processing, compared to other parts like the attention heads, and getting the attention value. That is done through the more complex mathematical number representation standards. It's a mouthful. Okay, but I think I get it now. Challenges with FP8, dynamic range. FP8 has fewer bits for representing numbers, so it can struggle with very large or very small values, outliers, quantization errors. When converting data to FP8, some information can be lost, which might impact accuracy if not handled carefully. How it works, okay, core operation FP8, okay. I think we get it, right? I think we get the concept. So what we're doing here, on top of managing the loads and then predicting 2 words ahead in the model as we're training, we're also, to make it cheaper, easier on computation, easier on memory, we're using the FP8, which is using 8-bit representation of numbers as we do those processes to make it lighter on the model, where the accuracy that we get out of this is needed and necessary, and not more is actually required, not more complex representation is required. In other parts like the attention, where we're calculating the attention values, then okay, we might take it a notch up to 16 or 32-bit representation for those calculations to avoid that kind of loss, which at that time is necessary because you get higher accuracy for such heavy computation that takes place. So, I think we understand now the 3 concepts that made this model what it is today. Before I conclude on the paper, I always like to go and see the conclusion of the paper, what they say about it at the end before we wrap up this video. Now, I encourage you to really go through the paper if you're interested to go through the details. I read it before. Even at some point they talk about what they do in the post-training, and they cover really what they did when it comes to supervised fine-tuning, reasoning data, reinforcement learning. Again, here they talk about it, rule-based reward models, and basically this is how reinforcement learning happens, as we discussed before, where there's a kind of reward that is delivered to the model to show that yes, you're going to the right direction, keep going there, or you have to change ways and go somewhere else or try something else. So this is the rule-based reward model and model-based reward model. I mean, these are concepts that are interesting to learn and read through, but let's carry on to the conclusion. Okay, conclusion, limitation, and future directions. In this paper, we introduced DeepSeek V3, a large mixture of expert language model with 671 billion total parameters and 37 billion activated parameters, trained on 14.8 trillion tokens, in addition to the multi-headed latent attention and the DeepSeek mixture of expert architecture. It also pioneers an auxiliary loss-free strategy for load balancing and sets a multi-token prediction training objective for stronger performance. Now, I think all of us understand this statement and these concepts, which I hope you would conclude that I did my job in trying to give you more information around this model as we learn together. I'm learning with you. The training of the DeepSeek V3 is cost effective due to support of the FP8 training. So now we understand what is FP8 training and meticulous engineering optimization. The post-training also makes success in distilling the reasoning capabilities for DeepSeek R1 series of models. Comprehensive evaluation demonstrate that DeepSeek V3 has emerged as the strongest open source model currently available and achieves performance comparable to leading closed source models like GPT-4 and Claude 3.5 Sonnet. Despite its strong performance, it also maintains economical training cost. It requires only 2.7 million H800 GPU hours for its full training, including pre-training, context length extension, and post-training. The whole thing costs $5.5 million. While acknowledging its strong performance and cost effectiveness, we also recognize that DeepSeek V3 has some limitation, especially on the deployment. Okay, firstly, to ensure efficient inference, the recommended deployment unit for DeepSeek V3 is relatively large, which might pose a burden on small-sized teams. Secondly, although our deployment strategy for DeepSeek V3 has achieved an end-to-end generation speed of more than 2 times that of DeepSeek V2, there still remains potential for further enhancements. Fortunately, these limitations are expected to be naturally addressed with the development of more advanced hardware. DeepSeek consistently adheres to the route of open source models with long-termism, aiming to steadily approach the ultimate goal of artificial general intelligence. In the future, we plan to strategically invest in research across the following direction. So this is interesting. We will consistently study and refine our model's architecture, aiming to further improve both the training and inference efficiency, striving to approach efficient support for infinite context length. Additionally, we will try to break through the architectural limitation of Transformer, thereby pushing the boundary of its modeling capabilities. They want to make the Transformer architecture much better. We will continuously iterate the quantity and the quality of our training data and explore the incorporation of additional training signal sources, aiming to drive data scaling across a more comprehensive range of dimension. Now, this is interesting. I think, again, here they didn't give credit to what I assume is really high quality. They mentioned it, they hinted to it, really high quality data that they used. And I think China maybe is able to harvest such data at such scale to give us such a model. But clean or good quality data make things better and more optimized and easier and cheaper, I assume. We will consistently explore and iterate the deep thinking capabilities of our models, aiming to enhance their intelligence and problem-solving abilities. by expanding their reasoning length and depth. We will explore more comprehensive and multidimensional model evaluation methods to prevent the tendency towards optimizing a fixed set of benchmark during research, which may create a misleading impression of the model capabilities and affect our foundational assessment. So here you have it, folks. Took more than what I really set out to do in one video. So I was promising everyone who's following me to do these single paper kind of concepts faster. Honestly, I didn't want to skim it so fast that you don't get the value. I know this could benefit only 10 people. I'm okay to invest my time to benefit 10 people who are serious about this thing, who maybe don't have the time to read on their own. They just want to hear someone doing it and struggling with it on the go. The future ones, I definitely will keep trying, like our friends in DeepSeek, to make it better, shorter in terms of concepts. You know, I might in the future just simply have those concepts that we cover ahead of the paper in links in the description. Just refer you to read them, and then we just go to the paper. So that will make things maybe shorter for the video lighter. And then you'll have to invest some of the time to read into these concepts just to understand them. So when we go through a paper, you understand it. I hope you got value out of this video. This just tells us what these people did differently, and now it's clear to me what DeepSeek did differently than other models to do it much cheaper and much better. Honestly, I'm gonna definitely do a short on this. So with this, thank you for watching. Subscribe, it's free. Comment, more important than anything else for me. Like, share, and thank you for your time, and goodbye.
Subscribe to Daddy's channel. Give me the mic.